our next speaker is Krish. Krish, I took a liberty of shading the title, not removing it, not editing it, but shading it so that the focus is on sensitivity and detectability. This is still a work in progress in the sense that we have last data point to fill. So until then, it is still work in progress. So it's working with Dan and Ron Crouch of JEOL. Okay, so let us start with, when I was preparing for this lecture, I look back at ENC Ivan conferences and what have I talked in the past. So that was a first ENC user conference. That's the title of my talk, Beyond One. I circled the beyond. I wanted to talk about beyond even the quantitative NMR. That was the idea. Except the next several years, I was going backwards. I talked about time domain back to basics. And I talked about when to benchtop, which is a low field. And I'm one of the very few, probably still around, maybe one or two, who has used continuous field, CW NMR. Yeah. So I'm going back to basics. And today, even fundamentals of sensitivity and detectability in NMR. That's what I'm doing. So perhaps I'm going in the wrong direction, but that's okay. That's because I'm a chemist. Those who don't know me, I'm a chemist. I'm a synthetic organic chemist. The benefit of being a synthetic organic chemist doing NMR is if you ask me a tough NMR question, I can simply say, I don't know, I'm just a chemist. So I don't have to answer that question. Okay, so let's go back to basics. A sensitivity resolution, and I took line width also. Line width is basically width at the half height. And then I said, okay, these are the fundamental definitions that we use. Detectability is a question mark. How did it all start? We published a paper, Dan brought this up. We published this paper, and the initial submission of this paper, we actually made a statement in the discussion session. We did in the abstract, we said significantly better, this 2D craft, significantly better by a factor of 30x. It's not 30%, 30 times as much as a regular 2D NMR. We made that statement and we provided, obviously the paper provided all the evidence for that. But then in the discussion session, I also made a statement, craft PS processing does not increase intrinsic detectability. The idea was to say, I am not changing the time domain magnetization. That is what we are detecting. We are not changing that. Unlike pulse sequence-based experiments, where you change the magnetization in a type of experiments or pure shift experiment, you're changing, increasing the magnetization. I'm not saying that. Except those two statements looked, for those who are not with me in saying that intrinsic means time domain, it looks like a contradictory statement. Yeah. So one of the referee came back and then said, if that is the case, why don't you just say so in your abstract? And I didn't want to say that so in my abstract because I knew where I'm going. I didn't want to say that. So what we did in the revised submission was we took that phrase out. We took that entire sentence out because we didn't want to provide information when we don't have the full information. Except we just made a response saying that it's an important generic discussion for, that deserves an academic discourse. We made a sort of a philosophical statement saying that it requires a discussion, but we won't say right now that our detectability is still the same. Lo and behold, this paper got published on the 17th December, 18th, I put it in my LinkedIn, and one of my very close friends, who is big craft fan, sent me an email on the 20th, which is 2 days after, saying that, but the old folks, I've changed the word folks to folks, like me, remember when hours are needed to get spectrum of 5-to-1 signal to noise. Can it be improved? So that's a very interesting statement. That's exactly the academic discourse that I wanted. I wanted people to think about what is it that we can do with the same information content in time domain. So I immediately, not immediately actually, that's 4 hours later, very unlike of me, but I did answer saying that we can dig down to signal to noise of 2.5 to 3, in spite of the fact we typically go for 5 to 1. I regret that statement because I underestimated it. That detectability limit I'm saying 2.5 to 3 is an underestimation. I think we can go even further down. That's what I'm going to talk about today. Okay. Let's get back to textbook sensitivity in NMR. Sensitivity in NMR is you have the height against RMS noise. Classic ethyl benzene, we have been doing it for 50 years, 60 years, 70 years maybe, ever since NMR was used. That's our measurement of how a spectrometer performs, a probe performs against another probe, another spectrometer. No question about it. I'm not challenging that either. Detectability also in a textbook format is typically at a point where the signal is just indistinguishable from the background noise. And we put a number around it. We simply said typically signal to noise of 3 to 1 or 5 to 1. In the good old days, we actually used to sit there and draw a line in the chart paper, peak to peak noise, and multiply that by 2.5, divide that by 2.5, and peak height, and measure all this. This is fundamental NMR. This is how we have been trained to think of NMR. Yeah, typically, that's a signal to noise. Where did that number come from? 3 to 1. Why? Why is 5 to 1? That comes from fundamental statistics. Noise is random. The very fact noise is random is a normal distribution in statistics. So an RMS is equivalent to standard deviation when it comes to noise, because an integral of noise is 0. So 1 sigma, which is 1 standard deviation away, is 68%. That means only 68% of the noise falls within 1 sigma, plus minus 1 sigma. When we go to 2 sigma, 95%. What does that really mean? If you take a 1D spectrum, let's say 16K point, Fourier number 32K. There's a possibility of 50 points, noise points, higher than 3 sigma. That's basic mathematics, because that number is 99.7. 99.7% will be less, 0.3% would be more of the noise. This is statistics. So there has to be that many points would be there. 50 noise peaks can be over your 3 times RMS statistically. So then we can calculate for 3.3 and 4, and we can say definitely at 5, probability is less than 1 out of 16,000 points that it will be that there will be a noise peak. Probability is. In 2D, it's worse. In 2D, there's a probability of 1 point somewhere in the 2D spectrum, which is a 2K by 1K 2D. Because there's 2 million points there. There's possibility 1 noise peak will be higher than RMS, 5 times RMS. Yeah. So this is where we put a conservative estimate of 3 or 5 or 3.3, whatever. You are a conservative, make it 5. You are a liberal, make it 3.3 or 3, whatever you want to do. These are all coming from basic statistics. Nothing new, nothing. I'm not reinventing anything. Comes from a normal distribution of any random event. This NMR happens to be, a noise happens to be a random event. Okay, what else next? Actually, when I was doing this, there's a very interesting paper in all about circuits. Don't ask me why I'm reading electronics. The website. That's a website of electronic engineers. But it was a very interesting paper about how these things happen. What is a noise in electronics? So I just thought I would put that in there because that's a very interesting paper for me, because I just started to read that. So I'm going to go back to time and frequency domain. That's the two domains that we know of. So we pulse, we have these three signals. Equal magnetization. The vector, all three vectors, blue, green, and red vectors, have the same amplitude. So detectability should be exactly the same. I don't see why not. And they spin around and we detect it over a period of time. And we are, in the last 40, 50 years, we have been doing Fourier transform, get a spectrum. Except those three signals are not the same height. I just made a statement, all those three was equal magnetization. Detectability should be the same. So if I use peak height, I lost it. All three do not have the same detectability. So what's the problem? The problem is not that the magnetization is wrong or FT is wrong. The problem is frequency domain. We are measuring it from frequency domain. That's the mistake. Your detectability should not be from frequency domain. Here is another example. I took a singlet and just multiplied by some line broadening function, 6 different ways. Each one of them have different height. If we use a textbook detectability as 3.3 height, 3.3 or 5 over RMS, all these 6 have different detectability, except they are all coming from the same FED. So what did happen? I introduced a process-dependent sensitivity loss. This has nothing to do with your time domain. This is a process. I process that FID 6 different ways. So should the detectability be dependent upon process? That's a fundamental question here. Should it be? Perhaps not. Let me show you something more interesting. We just heard Jeremy, SSFE, steady state free precession is done with truncated FID. There is your 32K data point. Let's call that our standard, 100 to 1. 100 points, just normalized to 100. If I had collected only 2K points, that is 1/16th. Yeah, instead of 1.8 seconds, 100 milliseconds. If I do an FT, that peak height is only 30. FT, no processing, no weighting function, no line broadening, no nothing. This is a fact of life. FT. We don't like this truncated artifact. We just heard it from Jeremy also. So what do? We do a match filter. Guess what? It's now 1/6 of what we were originally had. Just because I have a truncated FID, why? Let's just ask the fundamental question of why. It's because we can't live with that. Even if you do a Fourier transform, we don't want to do a 2K Fourier transform, so zero fillet, and we do a Fourier transform, then we can't live with the truncation artifact. Then we put an apologization at the cost of giving up sensitivity, peak height. And then we want to say that I want to detect X microgram of sample. You want to now equate that to some kind of a detectability measure. That's the problem. So that is your problem. What if I do it? Let's do a more systematic study. This is a singlet, 32K points, 256 points. 256, not 256K. 256 points. I just do a Fourier transform with a Gaussian window. Without a Gaussian window, just do a Fourier transform. This is the pattern I have, peak height pattern. And we don't like this truncation artifact. We put an apologization. In this case, I put a Gaussian. That's the pattern I have. So at 256 points, this is where I am. Peak height, this is what I started off with. Just because I collected only 256 points, nothing more than that. And we know amplitude is point number 1. The moment you pulse, whatever the magnetization is the amplitude of that magnetization. So this is a problem. This is a singlet, this is a doublet, another example of doublet. Jeremy's data or SSFP type of data, we are dealing somewhere in the 100 millisecond of acquisition. So just because I collect less, I have given up sacrifice about 80% of my signal to noise. Peak height, signal to noise is peak height to noise. Just sacrifice just because I collected less number of points. Let's take a 2D, that's even worse. In 2D, your required dimensions are somewhere in this region, 150 to 200 millisecond acquisition time. You don't want to be doing it because for an HSQC, I can't turn on the decoupler. We just heard from some question about probe heating. We can't turn on the decoupler for too long. So we are restricted by the experiment. I have to collect only 150 millisecond because my C13 decoupler is too hot. And this is a homonuclear evolution dimension. This is where you are in 256 increments, whatever. C13, if it's a HSQC, you are somewhere in 5 millisecond acquisition time in the revolution dimension. This is a double whammy on 2D. I am projecting you a triangle going down in height. In 2D, it's a cone. It's going on broad on both sides. It's becoming broader in the evolution dimension, it's becoming broader in the acquisition dimension. Double whammy. That picture doesn't even tell you how much signal to noise from a peak height definition point of view. We are giving up. We just talked about, somebody's talked about probe, hot probe, cold probes. We talked about cryo probe. We spent $100,000 for a cryo probe. Go to the lab. First thing we do is carbon-13 HSQC. Shot ourselves in our foot with sensitivity. This is the real practice up until now. This is yet another problem for me. When we want to increase the peak or decrease the peak height, peak width, we simply say, oh, go back to the lab and run more increments. I have done that to my associates. It's too wide, go back to the lab and just spend another half a day, or just run an overnight HSQC. Just overnight HSQC. You want a sharp resonance, go overnight HSQC. So we want to go from here to here. I do that, and in the good old days, I just simply say, increase my number of increments. In the fancy days, do a non-uniform sampling, do aliasing, do Hadamard type of experiment, right? Guess what? All of them are increasing T1 max, the maximum point that you want to collect, T1 max. And we think that because I increase my T1 max, my peak is narrower. No, it's not. Your peak is narrower. It shouldn't be, because decay rate constant is the one that should dictate line width. Just because you collected longer number of points, the decay rate constant doesn't change. That's a natural Mother Nature phenomenon. It decays at the rate at which it wants to decay. You can't change that. You just collected longer points. Guess where we get that resolution is apodization. In the bottom one, we put a very strong apodization, that green line. That's why I cast this line width. In the next one, I'll put a minor apodization. That's why it is sharper. It's the apodization and the zero fill that we talked about 2 slides ago. Caused all this. Not because we collected more number of T1 increments. I'll show you that the reason. Here is what I want to avoid. There is really no reason. we need to do Fourier transform, because a magnetization that is spinning has 4 properties and 4 properties only, each magnetization. Amplitude, decay rate constant, which is the rate of change of amplitude, phase, the direction of the vector, and frequency, rate of change of phase. These 4 properties, by their definition, are orthogonal. They have nothing to do with each other. Rate of change of phase doesn't change just because you started 50 points later. Brian asked a question to Jeremy. Probe background. Don't use the first 50 points. Your probe background decays out by that time. Don't use the first 50 points. It's that simple. The answer was that simple. Kraft simply does that. Yeah. So the 4 parameters that describe all these magnetization that's going back and forth during your time averaging are equations. 2 exponential equations, double exponential equation. And that's what Bayesian does. It essentially says, I can describe each one of those magnetization with equations. And that, on a different scale, is a table. The same 4 properties in that equation. I am not a mathematician, but I can understand the table. I have an offset, which is the frequency. I have an amplitude, which is the magnitude of the vector. I have a decay rate constant, which is the rate of change of amplitude. And I have phase. All are 4 orthogonal parameters. Bayesian has been doing this for the last 35 years. That was published in 90s. That was published in 90s. What we did was coming late. We came to the game. I came into this game only in 2000s. I looked at it, that's fantastic. I want to use it. But I'm not interested in the mathematics of it. I trust Larry, or I just use it, and if it works, it doesn't work, it doesn't work. Except once I am in a tabular domain, I can play with the table. I can move around the numbers and generate different representations. Frequency domain, frequency along one axis and height along another axis is not the only representation of NMR. We don't have to live with that. We don't have to live with that. You can sort, combine, filter, search, group, whatever you want to do. Whatever you want to do with the table. So just like in the good old days, before 1992, we did change. If I want to change my representation as a CH2s down and CH3s up to do an inept experiment, guess what I do? Go to my pulse sequence instead of an S2 pulse, take inept. So changing the pulse sequence changes your frequency domain representation. Now we have another tool. Changing the sorting, combining, filtering, using NMR logical rules. We can change the representation. Not changing the pulse sequence. We don't have to. If you want to, that's okay. You just got yourself another dimension of NMR practice. A third dimension, not in 2D, 1D type dimension. A third domain that you can play with NMR. And that's what we are able to do it. So here is the, I have to run faster because I know Shelley came in and then walked away. See, there she is. So I'm going to go faster from here on, right? Here is 1.8 tabular to frequency domain. Here is one interesting NMR stuff that we can do, yeah? So I look at the doublet of a doublet, which is in the grayscale, and then I take this FID, convert this into the table, and I do some kind of a magic, and then find those four magnetization that describes those 4 singlets, 4 patterns in there, 4-line pattern in there. That's one. How do I do this? We'll talk about that in a minute. So I got 4. Those 4 represents those 4 signals there. Oh, sorry. I can simulate them all whichever way I want. I can simulate them individually. I can simulate them as a sum. I can simulate whatever I want. It gives me the same thing that I would get with an FT. Yeah, I can do something else too. Oh, sorry, I'm switching. I can use this trick. I can take the tabular domain and do something with that. I understand NMR. I want to apply NMR. I simply look at that 4 and say, that's a proton. That means they all is a single magnetization split into 4 resonances. So I have these 4 resonances in the table. Combine them back. Your NMR rule says that they are the one proton got split, one signal got split into 4 simply because there is a passive spin sitting around. I simply say the opposite. I have these 4 magnetization. I know it's a singlet. I know it's a proton. Add them together. Put them together. Add them together in a vector fashion. These are vectors. Just keep remembering that. Pythagoras discovered it long time back how to add vectors. Several centuries ago. I heard that it is actually Babylonian time. Pythagoras was outdated by Babylonians, I heard. But anyway, that's irrelevant. As long as I can do mathematics with it. There is a single vector now. I simulated. That's a singlet. All of a sudden, I did a pure shift. I did a pure shift without doing a pulse sequence change. Yeah, that's the beauty of it. Now, what happens in a truncated FID? I have a truncated FID, 2 pure shifts. That's a 1.82 seconds. This is a 455 seconds. Look at the red lines. They are pretty much the same. Whether I'm a truncated FID or not, the peak height is the same. Doesn't matter because this table doesn't tell me anything how long I should simulate. I can simulate as long as I want. I can simulate instead of 455 seconds, that's the input FID, I can simulate 1.8 seconds. 25 seconds if the magnetization survives that long. Sharp resonance. What the hell? This table doesn't restrict me. The moment I get to the table. Now come back to this. All these are truncated FIDs. Craft. If you go through craft, no loss. In both dimensions. In both dimensions. Okay, here it is. Here is one. Chris, you are cheating. Here is one magnetization that is shorter. That's because it's shorter. Why? You're looking at frequency domain. Don't look at the frequency domain. Look at the table. That's a shorter one, if you may. That's a even further truncated, 1.14, very similar to a 2D acquisition. It's shorter. That's because the line width prediction is wider, because it had a doublet. But is that the detectability? Detectability is amplitude. Look at the 3 amplitudes there. That's the detectability. So your detectability should never come from frequency domain. Detectability should come from a tabular domain or time domain. If you can do straight from time domain, that's okay too. Come up with a different way of doing it. I can do it with tabular domain. That's just what we did. A lot of these explanations are in the workshop I did 3 weeks ago. Eric has made a fantastic job of making that into a YouTube picture. It's available. Go to IVNMR. You'll be able to find the entire details of how we did this. I did see that. You took a good picture of me. Thank you. Those who are not there, generic pure shift craft workflow will be like this. I will go from any conventional homonuclear, heteronuclear 2D input. I will go through that. No process I have my hands on. That's Fourier transform of the T1 dimension, T2 dimension, craft F1 of the T1 dimension, and then inverse Fourier transform, and then do my T2. So it's a 3-step process instead of a 2-step FT2D. And you craft pure shift table represents singlet vector. Every cross peak is a singlet in both dimensions. I don't even want to call it a pure shift, multiplet pure shift. It is a singlet. It is a cross peak, resolved cross peak. It can be represented by a single magnetization vector. And that's the magnetization vector. I can have fun, describe it whichever way. I want to look at a toxin-OZ spectrum, sure. Take half this table from one and the other half the table, slap them together. I get toxin-OZ. 2D spectrum. Pure shift 2D spectrum. No diagonal toxi. I'm not touching the pulse sequence. It's just the table. I just go to the table and say, don't bother with any cross peak that has the same chemical shift in both dimensions. That's it. I get a no diagonal toxi. In other words, whatever you want to do, you can play with this here instead of changing the pulse sequence. This is the benefit of time domain, tabular domain. Okay, fast. Sensitivity, summarizing, it's a process-induced height loss. Sensitivity, you can keep it the way you want it. Even then, how do I compare sensitivity of one process with another process? It's not a signal, it's about the noise. It's about the noise. Noise is a measure of uncertainty. Noise is not real. There is no noise coming in. It is you are detecting signal at 12 points. And you have an uncertainty in that detection, period. That's noise. There is no noise coming in. You just, signal is coming in. Your hardware says, I can't detect it precisely. It's uncertainty in signal detection. So Dan Iverson put a slide where he said, make FID with noise. What's wrong in just doing I want a noise 2D. Go make this is a noise that I want, just make a noise 2D. What's wrong with that? Fundamentally, nothing wrong in that because every 12 point has an uncertainty. That's it. No signal. The moment I have a noise, I can add that noise to any 2D I want. Yeah. So here is a simulated FT 2D, FT 1D, no noise. I can add the noise that I want and compare that to a Fourier transform results. I can do that with 2D. Noise FID is a very useful feature. Very, very useful feature. Here is the reason. We did this. This is the final paper. In the paper, we actually put this in. Again, I ask you to go back to the YouTube channel to look at that. This is a signal to noise improvement you get, not detectability. These have nothing to do with detectability. This is just signal to noise. 60 times. That's a signal to noise in pure shift over signal to noise in FT. Over, not percent. In order to emphasize that point, we actually made that statement in the paper. It is not percentage because we all tend to talk about, I got 20% more, I got square root of 2 more. We are not talking about percent. We are talking about factors. And it's nothing new. It's nothing. I did not get anything. It's the same 2D data input. That means detectability in time domain is exactly the same because it is the same input. I just processed it differently. Why am I here? Okay, I won't go there. Let's go back to detectability now. The problem with detectability definition is we define that as though it is a sensitivity number. We define that by saying it's a signal to noise ratio greater than X is my detectability. That is a fundamental problem. We shouldn't do that. I don't want to do that. Let's put it that way. Because detectability is magnetization. Amplitude of the magnetization. Nothing more, nothing less. Okay. How do in craft, I already have the amplitude. You guys now realize where I'm going. Because that's the amortization. If I go to craft, all I need to do is look at the amplitude. Let's go So detectability is actually how low can I go? How low a sample can I go and still detect? I took an example of HSQC of brucine. Yeah, that's an HSQC of brucine, 1 milligram, 600 microliter chloroform in 500 cold probe. And then I focus upon that region. Why that region? That's the 6th lowest sensitivity peaks, peak height peaks. They are the shortest peaks that there is. Said, what if I take that as example? Not the methyl groups, not your aromatics. Let's take those methylenes. Let's take those methylenes. Come back to Dan's tool. I can make noise. So that's my first is the data as it is. Where is my, okay, that's a data as it is. I said, add double the noise. Just generate a 2D noise data and add it some way so that your RMS is now twice, 2 times RMS, 3 times, 4 times, 5 times, 6 times, 7, 8 times. So that is equivalent to, this is 8 times diluted sample given the same noise. What's that? Lot faster. 3 seconds. 3 seconds? Yeah. Make food noise, it takes you 3 seconds. Not even that. Maybe I'm not doing it right. 3 seconds. That's it. Dilution. I just did a dilution, 8-time dilution. 8 data sets I have. I measure, I now want a benchmark. Sensitivity-based benchmark. How low can I go? Yeah. So that's, for all those 6 peaks, these are your sensitivity numbers. Sensitivity numbers, signal height to noise, conventional processing. That's the number. We have the original rule of detectability is 3 times signal to noise or 5 times signal to noise. This is where 3 times signal to noise meets, that's where 5 times signal to noise meet. Because if you look at this bar, that's put at 5, this is put at 3. Yeah, I need to have 3, I can't have more than 1/3 milligram of sample in the same condition before I can confidently say that I can detect all the signals. That's what that means. Yeah, every peak there is above 3. This here, if I had done 5, which is what I should, because I just said conservative, I want to be 5 because this is a big 2Ds. This is where I should be. I did the same 8 samples craft. Now, I don't want to put sensitivity number here. I want magnitude of magnetization. I want the amplitude of these signals, which I have handle on because these are graph results. I have my amplitude. I can plot the amplitude. The same 6, I'm plotting amplitude. Now I don't want. How do I? What's the minimum I can go? Go back to noise statistics. Uncertainty. 5 times uncertainty. Uncertainty being standard deviation from where you are supposed to be. Sigma. 5 times sigma or 3 times sigma. I don't want peak height because we know peak height is a useless parameter. I have the amplitude. So the question is, how uncertain are these amplitudes? It's not the noise I'm looking for. I'm looking for how uncertain these amplitudes are. Because that comes from the noise. The noise is actually uncertainty in the data points. We just made all those connections. So uncertainty in the amplitude is that. The second line, actually. Average amplitude error plus minus standard deviation is that number. That comes from whenever it calculates amplitude, no mathematical formula calculates an amplitude number. It says, this is your amplitude plus minus this. Yeah, so I have the error. I have the standard deviation of the error. And so my 5 sigma, in the first case, if I use RMS noise, the first case, it will be 12.9. In the second case, which is the most ideal one, is 3.9. Because it's a standard error in the amplitude plus minus a standard deviation of that error. This one is the amplitude if the amplitude is equal to 1 RMS. noise in a Fourier transform world, right? That's halfway through. But even then, thank you. I'm done. I'm almost done. I trust you. I'm almost there. I'm almost there. I'm almost there. If I use the first rule, amplitude per RMS, and 5 times that, my minimum detection is 7x. I can go 7x out from dilution, in dilution. So instead of 1 milligram, I can have 140 microgram. I will get all of them above that standard, that 5 sigma. If I take the second one, which is more truer because it doesn't use Fourier transform RMS and all that nonsense. It just uses, this is my amplitude, this is my uncertainty in that amplitude. If you use that, I can go 8 times. That's 0.125 microgram instead of 1 milligram from that dilution study, right? How did I do it? So this is, I want to put this one. This is one of my favorite slide. So I have to put this one in. I will drink this a little bit later. So these are 3 just almost done. I'm only 3 more slides. 3 more slides. But this is an interesting slide. 3 interferograms. Here's a challenge to all of you. 3 interferograms, real and imaginary. Real is blue, imaginary is red. Why? I don't know. At that time, I had the real imaginary turned on, and so it gave me both, and I just took a snapshot of it. Fourier transform, conventional Fourier transform. Tell me which one has peak, which one does not, and why. There isn't anything that you can tell. This is the end of it. You can't say anything. That means detectability is pretty much low in this condition. Except Kraft says, aha, the middle one has a sinusoid, and it is that sinusoid. It's that peak. In reality, that is a peak. That peak is there. You can see that peak right there. But you can't be as certain about it because there's another peak right there. If you come here, there's another peak right there about the similar height. It is the uncertainty of finding something as a peak instead of as a noise. That's your problem. That's because you did a FT, and in order to do an FT, you need to do a zero fill. In order to do a zero fill, you need to do an apodization. One feeds to the other. And that's what you can do. We don't have, we thought immediately, okay, 150 micrograms, go make a sample, let's finish it up. Mother Nature looked at us and said, ha, that's not that simple. Chloroform is acidic. Brucine is basic. It doesn't like too dilute brucine. So the sample we picked is a wrong sample. The one when you dilute, all peaks becomes broad in a very dilute sample. So Drawn is going to make more clean chloroform. So we just got slowed down because we didn't think about Mother Nature saying that you are dealing with an acid and a base, even though I post-hoc with George Ola. Right? So what can I do? Fortunately, I had 2 data sets on the same sample. One on a 500 cold probe, another one on a 400 room temperature probe. The ethyl benzene number difference is about a factor of 5 or 6, somewhere between 5 and 6. So I said, okay, then this is equivalent to 6 times dilution. Right? Look at the spectrum. I don't even have to tell you which one is which. If I didn't put that text in there, you would never know which one is 500, which one is 400. What more do I want to say in this? The source of this signal is not, I did something. The source of this signal improvement, even signal noise improvement, is because no apodization. No apodization in homonuclear 2D, you get a pure shift for free in that dimension. In HMBC type, you get decoupling of heteronuclear coupling constant, homonuclear coupling constant, all of them in one shot. You get all that benefit. In Kraft F2, on the other dimension, No optimization. Pure shift. HMVC is decoupled. Go do an HMVC decoupled experiment. I challenge you. I challenge you. I have done 10 years, 15 years with Gary Martin on this. It's not that simple. It's not that simple. So those are the benefits that you have by just getting into the tabular domain. I think so. Detectability is really amplitude. Measure the amplitude. So what is the lowest amplitude I can measure with the uncertainty below 5 sigma? 5 sigma of the amplitude error, not 5 sigma of your RMS. That's where we need to finally make that one proof statement. It will be there very soon. The idea is this: tabular domain gives you something to do with it. Not just about getting pure shift. It's now to redefine how low can I go, better than how low can you go after Fourier transform. That's the difference. Yeah? I think there is a large number of, this is just a joke slide. There's a large number of misunderstanding, misinterpretations, misconceptions in the literature. No question, because we have lived in Fourier transform world. So I went and I did some research, found a whole bunch of statements that put a smile on my face. I thought I will share with you, except I also wanted to make sure that I hide the source of those statements so that you won't know who said that or where it was said. So I want to do an editorialization. That's what I have. I am allowed to do that now. Yeah, I am perfectly allowed to do that now. I think with that, I can drink my wine. Questions? Thank you.
Thank you, everyone. So why don't we make our questions to Chris as we all get up and have wine? Or any question? Any questions now?
I don't have a question, but I just wanted to compliment you and tell you that you can claim singularity in detection.
But if you think about it, right? I'm sorry. That Pradeep made a statement about, I don't know if I'm doing it right or not. I'll hold it like this. Okay. It's a singularity. That's a very interesting word. It is a singularity. In every 2D, what is your cross peak? Let's define cross peak. Within the uncertainty of your measurement, of how you can see that peak, multiplicity or whatever you want to call it, within that uncertainty of that blob, it is a magnetization that precesses in 2 dimensions at a particular frequency, plus minus whatever error. No more and no less. So cross peaks are nothing but a singular entity within the limits of your detection, within the limits of your processing, within the limits of your T1 points, within the limits of your T2 points. Within that limit, it is a singular vector. And my question is, why can't we describe that vector for what it is? It is a vector precessing in 2 dimensions at 2 different frequencies. So it's a singular in both dimensions, period. What are we losing by stating that? Are you losing coupling constant? No. Coupling constant is a bane in our 2D, not benefit. Most of your 2D coupling constant bothers the hell out of you after it did the magnetization transfer that you wanted, which is the pulse sequence. The moment you finish the magnetization, I want it out of the way. I don't even want to see it. And here is an opportunity to do that by just simply introducing another domain, time, tabular, frequency. That's the message that I'm trying to convey. Let's just add one more domain. Yes, all these arguments are dependent upon the fidelity of time to tabular domain conversion. Just like all our 50 years of evolution of NMR is dependent upon time to frequency domain fidelity by Fourier transform. We all know It has its limitation. Let's just face it. Fourier transform changed the world. I don't have any argument about that. I wouldn't be here if it weren't for Fourier transform, if you were listening to George in 1978. But then we say that we have a truncated FID. Our thought process is, how am I going to get around it? How am I going to add a process to it so that I don't have the truncation figures? How am I going to add something else so that I will improve it better? Perhaps we shouldn't do that. Perhaps. We are willing to give fidelity looseness in one process. I'm just saying, is 8:1, I said 8x dilution is perfectly okay. Is that the limit? I don't know. That is within the fidelity of Bayesian that I have. I am sorry, I'm just a chemist. Yeah, that. But if we take that jump, if you drink that Kool-Aid, yeah, if you drink that Kool-Aid, then there is so much we can do without living with the limitations, without living with the consequences of that limitation. I am not saying non-uniform sampling is bad. Of course, but all of this will work even here too. You can have a non-uniformly sampled data and get a better tabular domain. Yeah. Get a better tabular domain. You want to do an aliasing that works for you? Go ahead and do aliasing. Go through a tabular domain. So you have another place where you can play with your data. Less uncertainty, really. This is the process-induced uncertainty we don't have to live with. Don't have to live with. But then again, I'm a chemist.
Thank you, everyone, for coming. So this concludes our 10th Ivan workshop.